Welcome to our next chapter. This is chapter 2.2. It's going to be talking about our properties of water and why water is important for us in our everyday lives. So why is water important? Well, 3/4 of this earth is actually covered with water. This is an astonishing number because when we look at a map, the only thing we ever really focus on is the land, and that only makes up 1/4 of our total earth. The other 3/4 of it is covered in this water. We also know that every organism we know to this day needs water in some way to survive. Yeah, there are some bacteria that can go without water for a long time. They actually go into a state of dormancy where they're not really functioning. But when they need to actually fully function, they will need water in some way. So why? Why is water important? In us alone, water makes up more than 60% of our body. If we were to lose water, we would shrivel up and die. Water helps with digestion and any kind of chemical reaction we have going on in our body. So we'll talk next semester about photosynthesis and respiration, but one of the byproducts of cellular respiration is H2O, water. So one thing that we make through this process is water. Water helps us maintain homeostasis, so it helps us keep that internal environment constant. All of our crops need water to grow. It helps them grow and multiply, and then it regulates the climate. So it's going to tell us if an area is going to be warmer, if an area is going to be colder. We see this as precipitation. We see it in all different manners. Water is able to hold heat, which is a really cool thing, which is actually why our areas like Florida will stay a little warmer. So, the water molecule, talking about polarity. I'm not for sure how many of you guys have heard of the term polarity before, but polarity talks about almost a positive and a negative attraction between things. So electrons not shared equally in water. So electrons aren't shared equally in water. There's a bit of more of a pull from one versus the other. The electrons are strongly attracted to the 8 protons of oxygen. So this causes oxygen end of this molecule to become slightly negative and the hydrogen end to be slightly positive. So these polar compounds have an uneven charge. So there is no actual extra ion on it particularly. When you see H2O written by itself, it's H2O with not a plus or a minus, but there's this overall net charge that is a little negative. So water becomes an excellent solvent. So solvent is something that can dissolve other things. So if you were to put salt into your water for pasta, that's what we're talking about with a solvent. Vent, I always think of like an air conditioning vent. Sometimes they collect water because they get cold. So vent is what you're mixing it in. Solute is what's being mixed, and we'll talk about those more later. So it also makes it easier to dissolve other polar compounds and ionic compounds. One thing you'll learn, and the easiest way to remember it, is that like dissolves like. So a polar molecule is going to be able to dissolve another polar molecule, or an ionic compound. Ionic compounds dissociate into ions. So in our liquid of water, we don't just have all H2O. It's actually broken up into OH minus ions and H plus ions, and they are randomly connecting with each other and breaking off. So there's this free floating ions in our solution, along with stable water molecules. So as we begin to discuss the water molecule more, we need to get into the concept of hydrogen bonding. So we have an attraction of water molecules due to polarity. This is a weak bond. This polarity is a weaker bond. There are different things that hydrogen bonding allows us. Hydrogen bonding itself is a bond with hydrogen, and there are only a few elements that are actually able to do this and create a hydrogen bond. It actually makes a 7 looks like a 7 on your periodic table. All right, so if we look at our periodic table, we can see it here, that we have this CNOFClBrI. These are all things that are going to be able to make our bonds with hydrogen. So this whole 7 along here will make our hydrogen bonds. So these hydrogen bonds are special because they allow the water molecule to do some pretty cool things. So we have cohesion, which is an attraction of the particles of the same kind. And this is going to increase the surface tension of our liquid. So cohesion is going to be the attraction of water molecule to water molecule. This is the reason we have raindrops as compared to rain just kind of spread out all over the place. The attraction between itself. We have adhesion, which is going to be the attraction of water between something to something else. So this could be water on a plant, how you see it sticking onto it in the morning as dew. This also brings into the idea of capillarity or capillary action, and this is how plants use water. So water moves up through small little tubes inside of the plants, and they're able to do this going against gravity because of its ability to adhere or stick to the sides of these little tubes inside the plants. The heat capacity, so other effects of hydrogen bonds and polarity. So with the heat capacity, it has a very high boiling point, especially for a molecule that's so small. It has a higher freezing point. It's most dense at 4 degrees Celsius. It has a high specific heat. Water warms slowly and cools slowly. So this warming slowly and cooling slowly is actually the reason that it's able to keep places like Florida warmer, because it collects all of its sun and warmth throughout the year, through the summer, and then as we get to the winter, when it starts to get cooler, it starts to slowly release this extra heat into the air, which keeps the surrounding area warm. So the ability of water to absorb large amount of heat helps keep cells at even temperature despite temperature changes in the environment. So that's speaking more inside of us. So that's a little change inside our own bodies that water helps with. So now let's talk about a mixture. So a mixture is a combination of 2 or more substances. I'm sure you guys have talked about mixtures before, or if you've ever cooked anything at home, you've had to mix things together. Usually it involves solid ingredients. So there's no chemical change. We're not making a new substance. Each substance retains its own original properties. It's in variable proportions. Sometimes we have more of the one versus the other. If we're talking about salt and water, we usually tend to have more water than we do salt. It can be physically separated. So the biggest idea with a mixture is at the end we could have both pieces again. Talking about salt water, the way to get the salt out is we evaporate the water. Once we evaporate it, let it condense, then we have separate salt and separate water. And this is actually how they go ahead and sterilize water, is they will evaporate out anything that's bad, and they leave behind the nasty particles because they will not evaporate. A couple examples are pizza or a salad also. So as we continue on, we'll talk about solutions. So a solution is a mixture in which one or more substances are uniformly distributed in each other. So this is when we've mixed things together and we have some kind of uniform distribution. A solute, like I was saying, is the substance dissolved in the solution. So this is usually our solid. For example, in salt water, this is the salt. Solvent is the substance in which the solute is dissolved. So this is what we are dissolving it into. Again, like I said with the salt water example, this would be our water. The concentration is the measure of the amount of solute dissolved in a fixed amount of solution. All right, so if we continue to talk about our concentrations, some examples would be a 4% salt solution. So that's saying that 4 grams of salt is dissolved in enough water to make 100 milliliters. So a saturated solution is one in which no more solute can be dissolved. So if you've poured and poured and poured salt into water, and you notice none of it continues to dissolve, and you're going to start seeing more of it at the bottom of your glass, that means you've reached a saturation point. No more of that salt is able to be dissolved in that water. And then an aqueous solution is a solution in which water is the solvent. So seawater, fresh water, intracellular fluids when we talk about cells. So an aqueous solution usually is referring to one that has been mixed with with water specifically. All right, so suspensions. So some materials do not dissolve when placed in water, but separate into pieces so small that they do not settle out. So they're not going to be able to break apart and dissolve in the water. They kind of just separate themselves out in the solution enough, but they're not actually dissolved in there. So they're not mixing and forming new bonds with some of the free-floating hydrogens or the free-floating ions. Sorry, I was coughing. So suspensions are mixtures of water and non-dissolved material. Some of the most important biological fluids are both solutions and suspensions. So for example, blood is mostly water. It contains many dissolved compounds, but also cells and other undissolved particles that remain in suspension as the blood moves through the body. So these pieces never fully dissolve in the blood. They kind of just follow around and move around with the blood. Acids and bases. So this is, again, going to start talking about the dissociation of water. So dissociation is what I was talking about earlier. So this is the breaking apart of water molecules into two ions. So when water is on its own as a cup, it's not just H2O. It's actually a mixture of H plus and OH minus ions. And also, the H plus is usually H3O plus. That's just how it tends to form itself, along with some H2O. So dissociation is the breaking down. So it's our H2O going to our H plus and our OH ion. Acidity and alkalinity is the measure of the relative amount of hydrogen and hydroxide ions. So equal number of each is a neutral solution. So as we begin to increase the hydrogen, we become more acidic. As we increase our hydroxide ions, we become more basic. So more H plus, more acidic, more OH, more basic. So acid, more hydrogen ions than hydroxide ions. That's our sour taste. So if you've ever tasted lemon or citric acid, for example, we have HCl, which is hydrochloric acid. This is going to dissociate into H plus and Cl minus. While our base are more hydroxide ions than hydrogen ions, it's going to be a bitter taste. So this is our sodium hydroxide going into Na plus OH minus. The pH scale. So the pH scale compares relative concentrations of the hydrogen and hydroxide ions in a solution. So it measures the amount of H plus ions. This again, as we talked with Friends of the Fox, is on a range from 0 to 14. 0 is very acidic, and you rarely ever see anything that has a 0 acidic value. 7 is neutral, that's what our lake was. 14 is very basic, again, that's really high, and you usually don't see it too much. It can be in ammonia solutions, along with an acid. You can see it as a very strong acid, like hydrochloric acid or hydrofluoric acid. Each step of the pH scale represents a factor of 10. So every time you're moving up or down, it's actually based off of a logarithmic scale, and you'll do that more in chemistry, actually calculating them all. But everyone is actually a base 10 factor. So the pH 4 is 10 times as many hydrogen ions than a pH 5. So there's that many more as you move down one step. That's just the way to explain it. So this means it is 10 times stronger than a pH of 5. So every time you're going down, you're getting 10 times stronger than the previous level. Buffers. So buffers are very important because buffers control of pH is very important. It helps us maintain homeostasis. A buffer is a solution that resists changes in pH when small amounts of acid and base are added. So what this is going to do is if you have a buffer solution and you add in, I don't know, let's say some acid, it is going to try to level it out by creating more of these OH bonds or hydroxide ions versus our hydrogen ions. And it's going to try to level the solution out so that it doesn't become too acidic. And this is important because of homeostasis. So in our body, there are different areas that will try to do this to make sure that areas don't become too acidic or too basic. So enzymes have a narrow pH range and will destroy them. Blood must be at a pH of 7.4. So if these aren't kept at these areas, then we can go into, for blood, we can go into a ketoacidosis or alkalosis. And these are things that usually diabetics will suffer from, but it's an increase in the acidity or the increase of the base in your bloodstream, which can kill and harm your brain. So as I said, buffer solutions are solutions that are going to resist this pH change when small amounts of acids or bases are added. So pure water is usually around 7. You add in 0.01 molar of HCl. You have a 2. A buffer solution would maybe be around a 4.74. So it's going to try to balance it out. And it's going to try to make it so that the solution is more of a level. It's not as acidic or as basic. It's almost going to try to meet in the middle. All right, so that is it for this set of notes. Make sure you guys write down some questions you have, and we can talk about it on Monday. Have a good rest of your weekend, guys. Bye.